Welcome back, focused learners, to another explainer. Right now, we're tackling a massive headache that honestly almost every dev team faces at some point: large database refactors. Our core mission today is mastering the safe workflow for navigating these complex refactors without totally corrupting your local development environment. We're going to look at building an isolation model, but our absolute main focus today, the real game changer, is going deep on the precise routine you need to switch branches safely. Okay, here's our roadmap. 1. The migration conflict problem. 2. Why patching actually fails. 3. Building the isolation model. 4. Our main event, the branch switching routine. 5. Handling realistic development data. And finally, 6. Converging before the release.
All right, let's jump straight into Section 1, the migration conflict problem.
To really get this, you have to think of divergent branches like alternate realities, a multiverse, if you will, that absolutely cannot cross. In one reality, you've got your legacy branch history. This is the specific sequence of events that built your current production database. Initial schema, add a timestamp, add a source column. But meanwhile, in an alternate reality, you're working on this massive refactor on a totally separate branch, consolidating history into a new baseline, maybe adding some new tokens. Here is the massive danger. Pointing both of these distinct, valid histories at the exact same local database will inevitably lead to a mixed schema disaster. Think about it. If your refactor branch runs its baseline, and then you switch back to legacy and it tries to run 001 underscore initial underscore schema, it's going to crash because those tables already exist.
See, you've got to understand how your tools actually think. Migration tools just do not care if the final tables look kind of similar. They aren't looking at the end result and saying, close enough. No, they track the historical sequence. They identify migrations by their specific name and their cryptographic checksum. So if you cross these histories in a single database, the tool gets incredibly confused. Statements fail, and honestly what's worse is that some statements might partially succeed, leaving your database in this weird drifted Frankenstein state that belongs to neither branch.
Moving right along to Section 2, why patching actually fails. We have to talk about the absolute most common, yet dangerous band-aid developers try to use when they hit these exact errors. Look, we've all been there. You get a migration error because the table already exists after switching branches, and you think, I'll just throw an if not exists on MySQL. It is so incredibly tempting to just write that one simple line of code, silence that annoying terminal error, and just get back to work.
But guys, this is a trap. I want you to take this very seriously. Silencing errors with if not exists completely ignores hidden schema drift. The crucial point here is that while the table itself might exist, it could have entirely different columns or data types. Your legacy branch might have completely different nullability rules, missing indexes, or different foreign key delete behaviors compared to the refactor branch. If you just paper over the error, your application might start silently corrupting data or failing in truly bizarre ways later on, all because the underlying schema isn't actually what the code expects. Listen, migration errors are there to warn you. Do not just silence the alarm.
Let's look at the solution in Section 3, building the isolation model.
So how do we actually fix this architecturally? Well, it brilliantly illustrates the elegance of the isolation model. The good news is you do not need to duplicate your entire stack. Things like Redis or object storage, those can remain shared because they usually aren't tightly bound to strict relational schema histories. But for your actual relational data, there's magic in this setup. You use one single local MySQL server, but you have it host two completely independent databases. Think App Legacy and App Refactor. This keeps your branches perfectly safe, their migration histories stay totally isolated, and it remains incredibly lightweight on your local machine.
Let's look at exactly how to set this up. It's literally just a few steps. You start your local MySQL service, usually with Docker Compose. Then you open an interactive session as root. You run your standard create database commands for both app_legacy and app_refactor. And finally, you just grant all privileges to your application user. Quick pro tip here, always use placeholder credentials in your tracked environment templates. Never commit your real passwords to source control. But once this is set up, you've got two pristine, isolated arenas for your branches to safely play in.
All right, here we go. Section 4, the branch switching routine. This is the big one.
This is the absolute core focus of our explainer today. This is the specific, deliberate checklist required every single time you change branches. Think of it as your pilot's pre-flight checklist, okay? Do not skip these steps. Step 1, stop the app container, but leave MySQL running. Step 2, switch your Git branches. Step 3, and honestly, this is where people mess up, Update your db_name and database_URL variables in your local environment file so they point to the correct database. For instance, change it from app_legacy to app_refactor. Finally, run docker compose up using specific flags. -d, -no deps, -force, -recreate app. A plain restart is simply not enough because it won't reload those environment variables you just changed.
So why do we use these exact flags? This is literally how we build our foolproof workflow. The no deps flag is brilliant because it leaves MySQL and your other dependencies entirely alone. It doesn't even try to restart your database server, which saves you a ton of time. The force recreate flag, that's the absolute hero here. It forces Docker to spin up a brand new container, which guarantees it actually reads the updated database URL pointing to your isolated database. And specifying app at the very end strictly scopes the operation, so you are only tearing down and rebuilding the application itself. This takes a simple restart and transforms it into a completely clean environment swap. Now, before you even think about running a migration, look at this verification checklist. You absolutely must drill this rule into your daily habits. Your Git branch, your environment variables, and your migration logs must perfectly agree. If your Git branch says refactor, but you run printenv in your container and it says app_legacy, stop, do not migrate. Catching a mismatch here takes 2 seconds. Repairing a mixed schema because you accidentally migrated the wrong database takes hours. Triple check this alignment every single time. Moving on to Section 5, Handling Realistic Development Data. So a really common follow-up question is, well, if we have these empty, isolated databases, how do we get good data in there without mixing up our histories? You basically have 3 safe strategies. First, repeatable seed data. You write deterministic scripts that generate your test accounts and settings every time you spin up. Second, sanitize snapshots. You can restore a production snapshot into a temporary database, but, and this is absolutely vital, do not restore the source's migration history table. If you copy the history table over, you literally just recreate the conflict we've been trying to avoid. Finally, for really massive refactors, use explicit data transformations. You write versioned, restartable scripts to migrate your data safely into the new model. And finally, Section 6, Converging before the release. Let's zoom out a bit. How do we bring these isolated realities back together for a real production deployment? Remember, isolation is a development technique, not a deployment strategy. When you are actually ready to merge, you need a highly safe convergence plan. First, declare the main branch as the ultimate source of truth. Second, rebase or merge the latest migrations into your refactor branch so you resolve conflicts in code. Third, you must test against both an empty database to prove your new history works entirely from scratch, and a legacy snapshot to prove the upgrade path works for your existing data. Once you verify all that, you deploy normally. And only then do you delete those temporary branch databases. So, I want to leave you with this provocative thought to ponder. Are your development databases truly isolated right now, or are you just holding your breath, waiting for a mixed schema disaster on your very next Git checkout? Implementing this isolation model and rigorously following that branch switching routine we focused on is your ultimate defense. It keeps your development predictable, fast, and above all, completely safe. Thanks for learning with me today, and I'll catch you on the next explainer.